Study automatic extraction of moving objects from UAV-borne monocular images using multiview geometric constraints. Now let me begin with the purpose and motivation of us. The purpose of this study is to detect and track moving objects in real time using a MAV equipped with a camera. I'd like to explain why moving object detection using the MAV. The mobile sensing using MAV has two strong points. The one is the comprehensive and selective sensing in large areas, and the other is that it can observe the same object from multi-viewpoints. We'd like to make use of these strong points for moving object sensing using MAV. The first strong point enables the effective sensing in crowded places, and the second strong point enables the observation of moving objects with less occlusion. And such a system can be used for various applications, such as people counting or surveillance in large areas, or novel broadcasting for the sports. This is like our MAV continues to track a specific player or a ball in a sports field. And this can also be used as a camera work generation tool for filmmaking. However, there is a problem to be solved for moving object detection from MAV. This picture is the real image which was taken from our MAV. These green lines show the motions of each object in this image. As you can see in this picture, not only the moving car, but also these static objects seem to be moving. This is because our MAV itself is also moving. So for moving object detection from the MAV, we must distinguish these two kinds of motions: the motion of MAV itself and the motion of the object on the ground. So let me move on to the approach to solve this problem. Our approach consists of two major parts. The camera motion estimator part estimate the MAV's position and pose, or camera's position and pose, using input images. In this part, we use a vision-based camera localization method, PTAM. PTAM extracts feature points from input image, and then it determines camera position and pose based on these feature points. The colorful points in this picture are the feature points which were extracted from the images. And the yellow line, this yellow line represents the MAV's trajectory, which was estimated by PTAM. Next, I'd like to explain moving object detector part. This part is one of the most important parts in our approach. As I mentioned, for moving object detection from MAV, we must distinguish these two kinds of motions. For this purpose, we use the multiview geometric constraints. The first constraint we use is the epipolar geometry. Epipolar geometry is a kind of geometry in a stereo vision. At first, the camera is located here, and it is looking at static point X. This small x is the location. It's the location of the point X in the first image. And then, camera moves. This camera motion is parameterized by rotational matrix R and the translation vector T. These R and T are estimated by PTAM, as I mentioned, and what we want to do now is to predict where this point X can be found in the second image. At this stage, we have no information about the depth or distance to the point X. So X may be here or other points along this line. Now, if x is here, we will find it here in the second image. And if x is here, we will find it here. And if x is here, it will be found here. Intuitively, the location of x in the second image is constrained on a specific line, like this. This line is called epipolar line. So if x is a static point, then the x on the second image must lie on this epipolar line. This is the epipolar geometry. Using epipolar geometry, we can detect some moving points. Let's suppose the x is a dynamic point and it moves like this. In this case, the x in the second image can be found here. And in this case, the epipolar geometry can detect this point as a dynamic point because this point x is far from the epipolar line. However, there are some moving points which cannot be detected by epipolar geometry. Let's suppose the point x moves like this. In this case, the point x moves along the ray in the first vision, like this. The epipolar geometry cannot detect this point as a dynamic point because the point x on the second image is on epipolar line. To detect this kind of motion, we introduce the second constraint, named flow vector bounds constraint. In this constraint, the point x in the second image is projected to the second image using homography, and then we check the motion of the point x on the second image. This motion is called flow vector. And if length of this vector is too long, the point x is detected as a dynamic point. These are the two constraints we used in our approach. This picture illustrates the process of moving object detection using geometric constraints. At first, we extract feature points from the first image. In the same way, we extract the feature points from the second image, and then we track each feature, and green lines in this image show the result of the feature tracking. And then we check the geometric constraints at each feature. The white lines in this image represent the epipolar lines. And these blue lines around the car, these blue lines represent the distance between the feature to the corresponding epipolar line. As you can see in this image, the feature points which were extracted from the moving car violate the epipolar geometry because there are many blue lines around the car. And finally, we classify each feature point as static or dynamic based on a predefined threshold. To test our approach, we conducted an experiment using our MAV. In this experiment, a small camera is attached to our MAV Aerodon 2.0, and this MAV is controlled manually by a laptop. I show you the result. I show you the movie of the experiment result. In this movie, only the detected moving points are shown as red points. our approach worked correctly despite the unstable motion of the MAV, although there are some false positives. And finally, I mentioned about the future works. For detecting and tracking of moving objects, we need a clustering method to cluster detected dynamic points into a dynamic object, and we also need a tracking method to know the behaviors of detected moving point among multiple frames. And we are now surveying for the real applications of our study. For those applications, we may need to add some autonomies our MAVs. This is the end of my presentation. Thank you for your kind attention. Please.
In your setup, do you have any
yes.
with the epipolar lines, do you have any singularities? For example, if the motion is in line with the camera?
Oh, when the camera is not moving, the epipolar is singular. You mean?
And if the camera is moving, but in the same direction as the movement of the obstacle, of the object?
Oh, yes, yes. So your question is, does our approach works well when the camera moves along the moving object? Yes. Yes. In that case, our approach doesn't work well because of the singularity, and so we challenge the motion planning for to get the performance better, like MAV to make the MAV move various directions. Yes.
Yeah.
Did I answer your question?
Yes, thank you.
Please.
One question regarding PTEM. So for PTEM to initialize it, to get like really a metric rotation and translation to
Yes.
initialize the scale. So do you use like a standard approach by moving it in the beginning, or do you have like some online estimation of scale in PTEM?
Oh, your question is how do we measure the scale from the PTEM? Yes, right. In this approach, yes. I use the altimeter equipped with the MAV Aerodon 2.0, and using that height, that measured height from the altimeter, and the height which was measured from the PTEM, we combine them and estimate the scale. Did I answer?
Yep.
Thank you. Yes.
Yes, in one of the slides that you presented, there was image with all the white lines going in a point. This epipolar, when you show the epipolar.
This. Oh, yes.
How you select the central point of these white lines?
Sorry, center.
The center of these white lines.
Oh, sorry.
Yeah.
This center.
How you estimate?
Oh, to estimate. We calculate each epipolar line and draw each epipolar line, and as a result, this point is drawn. Sorry. Did I answer your question?
Is it the center of the image? Is it the center of the image where your middle point is?
Center of image.
Together, is it the center of the image?
Sorry, center of which image?
Center of the image that you're, I guess
Uh, oh,
I thought there was one more question, if we could, please.
Thank you for your very interesting presentation. Do you manage to do all the calculation on the board?
no, this is processed offline and desktop PC. Yes.
Heavy in terms of
Not heavy, because we'd like to use this in a real-time process in the future.